So I'm Jan. Hello, everyone. This is joint work with Matthias, Patrick, Flemming, and Hanne, all from DTU. Yeah. So my wife just got me an update that so Denmark is playing qualifiers for the World Championships, and they just scored. So feel free to give me more updates as we go along. All right. So this has been a long day, I realize, so I'll try to go easy on you. All right. What are these? They are arbitrary OCaml programs. Aha. So what do they do? I have no clue. I didn't write them. What we did was we wrote a generator that wrote them. Aha. So what good are they then? You may very well ask. Well, they could be handy for testing. Say, if you have two compilers, then you can test them against each other. How? Well, if you take one of these programs and you compile it with OCaml's bytecode compiler, you take the same program, you compile it with OCaml's native code compiler, and then you run the produced bytecode executable, you save the output to a file, you run the native code executable, save the output to a file, and then you diff. Well, any difference in that in that last output should make you suspicious, right? You're mad as a hatter. Well, we actually wrote a generator of OCaml programs that does exactly this, and we used it to test this difference property. And then we found interesting things, like this little gem that says, well, here's an application that's bound to k and then returns 0. Okay, so what does the application do? Well, the argument is just a unit. And this operator expression here is something that has the side effect of printing a new line, and then it returns a 2-argument curried function, but we're only applying it to one. So if you pass that to the OCaml's bytecode compiler and run it, well, as you would expect, a new line is printed and the result is 0. If you compile the same program with, and here I should say a previous edition of OCaml's native code compiler, you'd get 0. Effect went away. What happened is there used to be a bug that this effect was delayed until this closure would be fully applied, and in this case we never fully apply it, so we delay it indefinitely. Well, we found other fun stuff. Here's another example for you. So 0 divided by something, and the something being let, and then a useless let binding, predecessor of 1, that's 0, so it says 0 divided by 0. So again, if we feed it to the bytecode compiler, you get division by 0 exception, as you would expect. With the previous edition of the native code compiler, you would get 0. All right. So this work is really describing how we did this. If you're interested in bug stories, and well, I love bug stories myself, I encourage you to have a look at our paper. All right. So program generation. How do you do that? Well, first idea that springs to mind. Let's generate some arbitrary strings. You're being silly, Jan. Yeah, so a few of these will of course make it through the lexer and the parser. If you want to stress test those, perhaps it could be fun to throw a few of these into the mix, but for our purposes, yeah, programs have structure, right? All right, so let's do something that builds on the grammar. So here's a little grammar for you. So I want to generate an arbitrary expression following this grammar. So starting from nothing, I'll just choose one of these productions, and I could say, let's go with the function. Aha. Function, so I need to generate a variable name, n, okay. And then I need to generate a body. So I invoke the generator again, and okay, I generate an application, which means I'll then need to invoke it twice, once for the operator, once for the operand. Okay, so give me an operator. Any one of these 4 productions. Ooh, I got a string literal, and then, an argument. Well, I got a variable j. Okay, so as you recognize, few of these will make it through the type checker. We are applying a string here to a free variable. Yeah, or you can do variations of this, but bottom line is, yeah, you're still going to battle the type checker. So third refinement, and here, this is ICFP after all, so no ICFP talk without the simply type lambda calculus rules. So here I've just put an extra parameter, which is the type environment for the constants or literals. All right. So the third refinement in this chain of ideas is not due to us. It's due to Michael Palka and friends from Chalmers, who had this idea of, well, let's read the typing relation bottom up in this goal-directed manner. Say, generate me an integer program. Well, how can I do that? Well, which of the typing rules have a conclusion that unify with int? Well, certainly not lam, but the other ones do, and so I choose one of them, say, the application rule. Well, for application, I would then need to generate 2 things, something of function type and something of argument type, and then, well, I need to come up with a type, so for lack of a better type generator, well, we can just go with int. So now, generate me something of type int to int. How can I do that? Well, choose arbitrarily, say, the lambda rule. Okay, again, I'll need to generate a variable name, x, and then I need to invoke the generator again to generate a body in an extended type environment. And there, we'll just go generate a variable. So hooray, we've generated in total over here the identity function. How about the argument then? I need to generate something of integer type. Let's go with the constant 42. All right. So when I first read that paper, I thought, this is beautiful. This is engineered to generate something that will make it through the type checker. And the entire thing is parameterized by the input type environment, the initial type environment, and this goal type. We should apply this to OCaml. All right, well, in OCaml, the observed behavior of programs may depend on the evaluation order. And here's a little example for you. If you run this program or evaluate this program left to right, well, this is a left-hand side. So inside that application, we do the left-hand side first, two argument function closure value, and then we print a 0. Then we apply it to the first argument, and then we do finally print a 1. So overall, we get 0, 1 printed. If you do right to left evaluation, well, this outermost argument prints a 1, and then we go inside and then do the right of this one, and we get a 0. So we get something different, right? All the OCaml programs are saying, yes, Jan, read the specification. The language spec is very clear about this point. The evaluation order is unspecified. And this goes back to Xavier's tech report from 1990. about how he could ingeniously save closure allocations by doing right to left evaluation. So go read that paper, it's a classic. All right, for testing purposes, it's sad, right? Because then it means that, well, anything we would get out, any difference of these may just be noise due to this loose specification. So what can we do about it? Could we somehow avoid generating such programs in the first place? It would be nice, wouldn't it? Okay, let's go simple. I'll go with one extra bit in the type system. I'll extend it to a type and effect system, so I'll go crazy. I'll add 1 bit. And the 1 bit says, well, this, when evaluating this sub-expression, it may have a runtime effect. So literals here, they may have an effect. Variables, when you evaluate them, they may have an effect. It's a free variable, so you can put either the true or the false bit in there. I'll annotate the typing arrow with a little effect as well, saying, well, once I apply this function, it may have this effect. And finally, what you were waiting for, the application thing, the application expression. When you evaluate an expression, well, it may have an effect if either of these constituents may have one, right? We are almost there, because now we have we have 2 bits for an application. We have one for the operator, one for the operand. Now, there may be evaluation order dependence if they may both have, there may be evaluation order dependence if both of them may have effects. So now we go crazy. We add that 2nd bit. Now we have 2 bits. An effect bit and an evaluation order dependence bit. And then we can refine that type and effects relation similarly. And then this funny application arrow says, well, that propagates that information from the effects bits to the evaluation order dependence bit. All right. So I'll throw a bit of formalism in here. So formally, how do you describe that kind of loose definition regarding evaluation order? Well, you could do 2 rules for evaluating the sub-expressions of an application, saying, well, I can choose to take a step in the left or in the right. And over a sequence of such things, of course, you can then also do interleaved things. And here, the little annotations over the transition arrows represent the runtime effects. And then you can do a traditional preservation in progress result, proving the soundness of the underlying type system. Of course, that says nothing about the actual effects. So we have 2 more theorems that say something about those. One saying, well, the first bit, the effect bit, correctly anticipates the runtime effects, and similarly the EV bit correctly anticipates the evaluation order dependence. Enough formalism, enough refinement. Now, well, we have an effect system, and then we can read it bottom up, like Michael Palka and friends, except now, well, we don't just have a goal type tau, we also have a goal effect. And if we choose 1, 0, it means, well, generate me a program that may have effects, but it may not, it's not allowed to have evaluation order dependence. Great. So that's the thing we implemented. So this prototype implementation, we just use int, and then we print that the result of evaluating that integer to ensure some output. All right. So we actually refined that that signal to noise ratio to really give us something. Now and then you can sit down with daring hands, write that message to the INRIA guys. Look, guys, I think I actually found something. wouldn't it be nice if we could automatically simplify that thing into this? We actually can. We can shrink that one into that one. And the way we do it, I only have one slide to tell you. Well, we do a type-preserving shrinker. And it's composed of doing just a sequence of little shrinking simplification steps. And here's just a selection by example. So if you have a large literal, well, you could shrink that one. If you have any sub-expression here of type int, well, we can replace it just by a literal. Here's an immediate application. Well, we can rewrite that into a let binding. Of course, you also shrink recursively. So in this example here, I'm shrinking the body of the lambda, and then in this one, I'm removing an unused let binding. Yeah. There was one more. This one, I'm just simplifying a conditional into one of the branches. All right. So in summary, I presented an effect system that decides this evaluation order dependence. We have a formalization of a little core of it, which we proved sound. We then used this effect system to drive a program generator inside this prototype compiler tester, including the shrinker that would allow us to cut down the produced counterexamples. Overall, I think, well, it's really a success of and a celebration of the results coming out of this community, because we're combining, QuickCheck for one thing, and type and effect systems from this community to develop something. We found actual bugs in there. I should say they have all been fixed for the latest release. So a shout out to Mark Shinwell from Jane Street for doing that. Thank you, Mark. Yeah. So all in all, I think this shows potential for sort of next generation quality assurance of compiler optimizations. So here at the very end, I want to just, so here I am inside a Docker image. It's a Linux machine with a previous version of OCaml, and here I'm just going to run the tester here with a known seed. So any dot you see there is a program being generated and compiled with both of them, and their results being compared. And that first X marks the first difference. And from here on, you then see a chain of attempts to shrink it. Yeah, thank you.